Imagine for a second, right, that all of scientific knowledge was just boom wiped out in some massive cataclysm.
Like completely gone.
Totally gone. And you, the listener, you are tasked with passing on just one single sentence to the next generation of humanity to help them rebuild their understanding of reality.
Just one sentence. That is a lot of pressure.
Right. But what do you tell them? According to one of the smartest physicists to ever live, you don't give them complex equations, you don't give them deep philosophy. You basically just tell them that absolutely everything is made of jiggling little dots.
Jiggling little dots. I love that.
Yeah, so welcome to a brand new deep dive. Today our mission is to grab a shortcut to understanding the fundamental rules of the universe around you.
And we've got some incredible source material for this.
We really do. We are pulling insights from a totally legendary text. It's called 6 Easy Pieces by Richard Feynman.
Right. The famous Nobel Prize winner.
Yeah, but he wasn't just a physicist. He was, a bongo player, a safecracker, and a brilliant teacher who absolutely despised academic jargon.
Which makes him the perfect guide for this.
Exactly. So we're going to use his mental models to decode the invisible machinery running the reality that you interact with every single day.
It is a fantastic mission. And to really, set the stage for how Feynman approached this, I want you to imagine that the universe is a giant, impossibly complex game of chess.
Okay, I'm with you.
And it's being played by the gods, right?
Yeah.
We don't know the rules of this game at all. We are just mortals who are allowed to watch the board.
So we're just spectating.
Exactly. But by watching long enough, we eventually start to figure out a few things. Like, we notice that a bishop always stays on a red square. Or we see that knights move in that awkward L shape.
Right, the patterns.
Yeah. This deep dive is about uncovering those hidden fundamental rules of the cosmic chess game. Like the absolute bedrock principles of physics, but completely without getting bogged down in the math.
Okay, let's unpack this by going right back to that cataclysm scenario, the ultimate, cheat code for the universe.
One sentence.
Yeah. Feynman actually had a very specific answer for what that one surviving sentence should be.
He did. He called it the atomic hypothesis. Feynman believed that if you could only pass on one piece of information, it should simply be this, that all things are made of atoms.
The jiggling dots.
Exactly. Little particles in perpetual motion, attracting each other when they're a little distance apart, but repelling upon being squeezed into one another.
It sounds almost, I don't know, too simple on the surface, but the way he asks you to visualize it is just staggering.
Oh, the water drop analogy.
Yes. So he asks you to imagine a tiny drop of water, just 1/4 of an inch across.
Pretty small.
Right. But if you magnify that drop 2,000 times, it is suddenly the size of a large room. And inside, you'd see it filled with squirming, single-celled organisms darting around.
Paramecia, right?
Yeah, biologists call them paramecia. But he says, don't stop there. Keep going. Magnify that drop 2,000 times again.
So now we're at what? A massive scale.
Now that single drop of water is 15 miles across.
Wow. And at that massive scale, the smooth, continuous water you started with, it just doesn't look smooth anymore.
No, it's chaotic.
It looks teeming. It looks almost like a massive swirling crowd at a distant football game.
And if you zoom in one more time, so magnifying it 1 billion times in total, you finally see the individuals in that crowd.
The molecules.
The water molecules themselves. And they look a bit like Mickey Mouse heads.
Right. The one larger oxygen atom with the 2 smaller hydrogen atoms stuck to it like ears.
Like little ears. And the craziest part is they are never, ever sitting still. They are constantly jiggling and twisting and bouncing and pulling on each other.
Perpetual motion.
Yeah. But wait, if everything is just atoms bouncing around like a giant game of cosmic billiards, then my understanding is that heat isn't really a thing at all, right?
Oh, that's right.
It's just a measurement of how fast those Mickey Mouse heads are moving. And if they move fast enough, do they just fly apart into steam?
That is the exact mechanism of heat. When you turn on the stoves to boil that water, you aren't adding some invisible magical substance to it.
Right.
You are simply adding kinetic energy. You're violently increasing the jiggling motion of those molecules.
Making the crowd angrier.
Essentially, yes.
Yeah.
And eventually, they jiggle so furiously that the natural attractive forces holding them together just aren't strong enough anymore.
So they break.
They literally break free from their neighbors and fly apart into the air. And that is what steam is.
That's crazy.
But this invisible atomic jiggling also perfectly explains everyday, mundane things like Think about why you blow on a hot bowl of soup to cool it down.
I mean, I always just assumed I was blowing the hot air away from the bowl.
Most people do.
Yeah.
But you are doing something much more specific at the atomic level.
Oh, really?
Yeah. The molecules in your soup are jiggling at different speeds. Occasionally, one molecule near the surface gets bumped by its neighbors with an extra burst of energy.
Like a springboard.
Exactly. Yeah. Just enough to break the chemical attraction and escape into the air above the bowl. That is evaporation.
Okay, makes sense.
But because it is only the fastest, most energetic molecules that have enough energy to jump ship, the ones left behind in the soup are the slower ones.
Oh. And slower motion literally equals lower temperature.
Right. So the soup cools down. When you blow on it, you are physically sweeping those escaped, fast-moving molecules away so they can't bounce back into the liquid and transfer their heat back into the soup.
I am physically separating the fast atoms from the slow atoms with my breath. That is a wild mental image.
It really changes how you look at dinner, doesn't it?
It does. But wait, if these atoms are just positive and negative charges violently pulling on each other, it seems like a miracle they don't just collapse.
What do you mean?
Well, I mean, opposites attract, right? Why doesn't the negative electron just crash straight into the positive nucleus and end the whole game?
That very question broke classical physics and completely forced humanity into the quantum era.
Really? Just that?
Yeah. Because if Newton's classical laws applied down there, the electrons absolutely would crash into the nucleus. The atom would implode.
So why doesn't it?
It survives because of one of the most counterintuitive rules in science, Heisenberg's uncertainty principle.
Right, I've heard of that.
In the quantum world, the universe simply refuses to let you know exactly where a particle is and exactly how fast it is moving at the same time.
Okay.
If an electron were to crash into the nucleus, it would be trapped in a tiny, precise location, and it would have stopped moving.
Yeah,
Right.
because it crashed.
Right. Which means we would know both its position and its momentum with absolute certainty.
And the universe just says, no, that's illegal.
The universe physically forbids it. To avoid violating the uncertainty principle, the electron demands a certain amount of, room to jiggle.
Room to jiggle.
It maintains a minimum amount of motion and a fuzzy, smeared-out location.
Yeah.
I mean, the chair you are sitting on right now feels incredibly solid, but it's actually almost entirely empty space,
Which is always so creepy to think about.
held up by electrons vibrating furiously because the fundamental laws of nature won't allow them to stand still. That quantum fuzziness is literally what gives matter its physical size.
Here's where it gets really interesting,
Yeah.
because this destroys the classic idea of what science even is.
Oh, absolutely.
We are all taught in high school that science is about strict predictability, like a clockwork universe. If you drop a ball in Stockholm and drop the same ball in Quito, you expect the exact same predictable result.
The exact same.
But Feynman points out that because we can't know the exact starting conditions of these quantum particles, we mathematically cannot predict their exact outcomes.
Also, we can't.
If you have an atom ready to emit a photon of light, you cannot predict exactly when it will happen. You can only predict the statistical probability of it happening.
And let me tell you, it was a massive philosophical shock to the scientific community.
I bet.
Many brilliant minds, including Einstein, hated this loss of determinism.
Right. God doesn't play dice.
Exactly. They felt it turned the universe into a casino. But as Feynman stresses, the ultimate test of any scientific theory isn't whether we like it, It's the experiment.
Right.
And experiments repeatedly tell us that nature, at its microscopic core, is statistical and chaotic. We just have to accept the rules of the chess game as they are played, even if it totally offends our common sense.
And accepting that chaotic reality led to things getting incredibly messy for a while.
Oh, very messy.
Because we zoomed in, found this fuzzy uncertainty, and then we realized there are a whole bunch of extra weird pieces on the chessboard.
We really thought we had it figured out. We
Yeah.
used to think the atomic world was neat and tidy, just protons, neutrons, and electrons.
The classic trio.
Yeah. But as our particle accelerators got more powerful, we started smashing these particles together at blinding speeds.
Just to see what would happen.
Right. And instead of breaking neatly, they spawned a confusing zoo of new subatomic particles.
A zoo.
We found muons, which act just like electrons but are bizarrely heavy. We found pions, which acts like the heavy cosmic glue holding the atomic nucleus together.
So it wasn't just the trio anymore.
Not at all. Suddenly, the universe wasn't just made of 3 simple building blocks. We had over 30 fundamental particles. It was total chaos.
Oh.
This raises an important question. If the subatomic world is that fuzzy, chaotic and overflowing with unpredictable particles, how do those messy pieces cooperate to build something as highly structured and reliable as the human body?
Okay, let's look at exactly how this atomic machinery builds biology, because Feynman uses the example of smelling a flower.
That's a great example.
When you lean in and smell violet, it feels like this ethereal, emotional experience.
That's poetic.
Yeah. But mechanically, it is just a specific, highly complex shape of atoms that has accidentally jiggled its way through the air and physically bumped into the chemical receptors inside your nose.
And that demystification applies to every function in biology.
Everything.
For a long time, humanity believed living things possess a magical life force that completely separated them from rocks or water.
Right, like we were somehow special matter.
But biochemistry revealed that just isn't true. Everything a living creature does, atoms do. Feynman outlines the Krebs cycle, which is the engine inside our cells that generates energy.
High school biology flashback.
Right. But it's not magic. It's a brutal mechanical disassembly line. Enzymes grab molecules from the food you eat, physically rip their carbon and oxygen bonds apart, and restitch them into new shapes.
Release an atomic energy in the process.
Exactly. It's just physical laws rearranging matter.
And I feel like the ultimate example of that is DNA. I really love how this text demystifies genetics.
It really does.
Because DNA is a literal physical blueprint. It's two chains twisted together made of 4 chemical units we call A, C, T, and G.
The alphabet of life.
Right. And it's not just that A magically pairs with T. It's that the specific arrangement of protons and electrons on those molecules creates actual chemical attraction and repulsion.
It's physical.
Yeah. They are physically forced to snap together like a magnetic lock and key. When a cell divides, the chain splits down the middle, and floating spare atomic parts in the cell physically snap into place to build a new, perfect complementary chain.
It's basically a self-replicating atomic zipper.
Yes. It's so cool.
It is entirely mechanistic. But the beauty is that these implications stretch far beyond the microscopic biology of a cell.
Oh, absolutely.
If we scale all the way up to the macroscopic world of astronomy, we find the exact same atomic machinery at work.
Which brings up one of my favorite revelations. How do we actually know what a star is made of if we've never sent a probe into one?
It's a great question.
It's because we can analyze the frequencies of light they emit. Each element emits a specific, unique chord of light when it burns.
Like a fingerprint.
Exactly. By analyzing starlight through a prism, we realize that the stars are made of the exact same atoms we have here on Earth. I mean, helium was discovered by analyzing the sun's light before it was ever even found on our own planet.
Which is just incredible to think about.
But I want to push back on this for a second, because I hear this critique a lot.
Okay, what is it?
Doesn't reducing the entire universe from a living, breathing frog to a giant ancient star down to just jiggling globs of atoms sort of ruin the poetry of it all?
Ah, right.
Doesn't it make the universe feel cold and mechanical?
Feynman fundamentally disagreed with that perspective. He argued fiercely that scientific knowledge only adds to the beauty and the mystery of the world.
How so?
Well, think about what the atomic hypothesis actually tells us about our connection to those stars.
Okay.
The heavier atoms currently sitting inside your body, like the carbon in your DNA, the iron in your blood, the calcium in your bones, they couldn't be formed in the gentle warmth of the early universe.
Right, it wasn't hot enough.
No, they had to be forged, literally crushed together inside the unimaginably hot, dense furnace of a star's core.
Wow.
And the only way those atoms got to Earth was because that star eventually died, exploded in a massive supernova, and violently spat those heavy atoms across the empty galaxy.
So we are literally recycled star stuff.
You aren't just looking up at the night sky as a separate observer. You are intimately physically composed of it. Knowing the mechanism of how you were forged doesn't subtract from the poetry. It creates a far deeper, more awe-inspiring poem than anyone could have invented without science.
That is beautiful. So if everything from the physical lock and key of our DNA to the exploding furnace of a supernova is just these same atoms interacting, there have to be overarching, unbreakable constraints governing the entire system.
Yes.
Like they can't just bounce around doing whatever they want.
There are very strict constraints. And this brings us to the great conservation laws of the universe, the most famous of which is the conservation of energy.
The big one.
It is the unbreakable law that energy cannot be created or destroyed, only transformed from one state to another.
And to explain this without getting lost in equations, Feynman uses an amazing analogy about a kid named Dennis the Menace and his toy blocks.
There's a classic Feynman analogy.
Listener, picture this. Dennis is a kid with absolutely indestructible toy blocks, and he has exactly 28 of them.
Not 27, not 29.
Exactly 28. Every night, his mother comes into his room and counts them. There are always exactly 28.
No matter what complex castle or fort he builds that day, the total number of blocks on the floor remains constant.
But one day, she comes in and counts only 27 blocks.
Oh, no.
Right. She searches the room and eventually finds one hidden under the rug. The next day, she counts 30.
Where did they come from?
She investigates and finds that a friend came over to play and left a few of his own blocks behind. So she gets rid of the extra blocks, locks the door, and closes the window.
Which is the crucial requirement for the conservation of energy. It has to be a closed system. No new energy coming in, no energy leaking out.
Exactly. But then Dennis gets sneaky. The mother comes in one day and only counts 25 blocks on the floor.
He's hiding them.
He has a locked toy box, and he refuses to let her open it. But the mother is clever. She knows that an Atty box weighs exactly 16 ounces, and each block weighs 3 ounces.
She's doing the math.
She weighs the box, subtracts the 16 ounces of the empty box, divides the remaining weight by 3, and perfectly calculates that there are 3 blocks hidden inside.
Brilliant.
Later in the week, the bath water is terribly dirty, and she can't see the blocks in the tub. But she knows the original water level was 6 inches, and each submerged block raises the water by 1/4 of an inch.
So she checks the water level.
She measures the new height of the water, does the math, and again accounts for the missing blocks.
Wait, so she is basically doing forensic accounting without actually seeing the blocks themselves.
If we connect this to the bigger picture, the blocks in the story represent energy. But here is the massive, mind-bending twist in Feynman's analogy.
Okay, I'm ready.
There are no physical blocks.
Wait, what do you mean there are no blocks?
In physics, energy isn't a physical blob. It is not a tangible substance you can hold in your hand or isolate in a jar.
It's not. No, it is a completely abstract mathematical constant. When physicists calculate the kinetic energy of a moving car, the heat energy of a fire, or the mass energy of Einstein's EMC squared, they are basically weighing the toy box and measuring the dirty bathwater.
Oh, wow.
They are using completely different mathematical formulas for different situations, but when they add all the final numbers up across the entire universe, the total amount never, ever changes. It is always 28.
So what does this all mean? It means the universe keeps a flawlessly balanced checkbook, even if we have no idea what currency it is actually using.
Exactly.
We just have the mathematical formulas to track it. And that reliance on mathematical abstraction is also true for the other great constraint ruling the board, which is gravity.
Yes, gravity. The ultimate invisible tether keeping the universe from flying apart. You know, Isaac Newton's greatest revelation wasn't just that an apple falls to the ground.
Right, everyone knows things fall.
It was realizing that the force pulling the apple is the exact same force pulling on the moon.
And the mechanism he used to figure this out is brilliant. He realized the moon is actually falling toward the Earth identically to a bullet fired out of a gun.
Like a projectile.
Yeah. If you fire a bullet horizontally, it travels forward, but gravity immediately starts pulling it down toward the ground at about 16 feet per second. But the Earth isn't flat, it's a sphere. It curves away.
So if it goes fast enough...
Newton realized that if you shoot that bullet fast enough, by the time it falls 16 feet downward, the Earth has curved 16 feet away beneath it.
It would constantly fall, but constantly miss the ground.
It would orbit. That is exactly what the moon is doing. It is moving sideways so fast that as it falls, the curved Earth just keeps dropping away underneath it.
The moon is falling about a 20th of an inch every second. And Newton deduced the precise math behind this invisible pull, the inverse square law of gravitation.
The inverse square law?
It simply means that the gravitational force gets weaker the further away objects are, specifically by the square of the distance.
Okay, so if you double the distance...
If you double the distance between two planets, the gravitational pull between them drops to 1/4 of what it was.
And that single, elegant mathematical rule explains an unbelievable amount of the cosmos.
It explains the rising and falling of the tides on Earth, dragged by the moon's pull. It explains the elliptical orbits of Jupiter's moons.
Galaxies too, right?
Yes. It explains why billions of stars hold together in those beautiful, spinning, spiral galaxies. It even allowed astronomers to discover a completely hidden planet using only a piece of paper.
Oh, the Neptune story.
Yeah. In the 1800s, Astronomers noticed that the planet Uranus wasn't moving perfectly according to Newton's equations. It was wobbling slightly in its orbit.
Something was messing with it.
Exactly.
Yeah.
Two mathematicians trusted the law of gravity so deeply that they calculated there simply must be an invisible, undiscovered, massive planet pulling on Uranus to cause that specific wobble.
That is wild.
They told astronomers exactly where to point their telescopes based purely on the math, and boom,
Yeah.
there was Neptune.
That is the ultimate flex of theoretical physics. Trusting the math so much you discover a hidden planet in the dark.
It really is.
But Feynman points out a lingering fundamental mystery here. We know the math of gravity flawlessly. We can launch satellites based on it. But we have absolutely no idea what the machinery of gravity actually is.
We really don't.
We know how it pulls and how much it pulls, but we don't know what is doing the pulling. There are no invisible gears or physical strings connecting the Earth to the moon.
That is the hallmark of fundamental physics. We have quantitative, highly predictive mathematical laws that describe the universe with astonishing precision. But the underlying mechanisms, the actual gears and levers of the cosmos, often remain completely hidden from us.
We're just spectating the chess game.
We are still just mortals, sitting outside the board, watching the game.
Let's step back and look at the whole board we've covered today. We started by zooming way into a single drop of water, magnifying it until we saw the chaotic, perpetual jiggling of atoms.
Mickey Mouse heads.
Yeah. We learned how the fuzziness of quantum mechanics keeps those atoms from collapsing in on themselves, creating a universe built on statistical probability rather than rigid clockwork destiny.
Right.
Then we scaled up, realizing that everything from the chemical lock and key of our DNA to the explosive death of a star is just those exact same atoms rearranging themselves. We recognize that we are entirely constructed of recycled star stuff, and all of it is operating under the invisible, unbreakable mathematical constraints of energy conservation and gravity.
What's fascinating here is that nature doesn't care at all about the neat little categories we create in our university departments.
What do you mean?
Nature doesn't separate physics from chemistry, from biology. Feynman famously noted that if you look closely enough at a simple glass of wine, you see the entire universe.
Wow.
You see the physics of fluid dynamics as it swirls. You see the chemistry of fermentation. You see the biology of the yeast cells. You see the geological history of the Earth that provided the nutrients for the grapes. And you see the atomic legacy of the stars that forged the carbon inside it. It is all one continuous, magnificent, deeply interconnected phenomenon.
It truly is. And to end this deep dive, I want to leave you with one final provocative thought that builds on everything we've just explored. Think about what you, the listener, actually are.
This is the crazy part.
You are a massive, non-repeating pile of atoms. You are trillions upon trillions of tiny dots that were forged in the cores of stars and have been bouncing around blindly, without purpose, for billions of years.
Blindly jiggling.
Yet somehow, through the relentless application of these physical laws, those blindly jiggling atoms have arranged themselves in a pattern so staggeringly complex that you are currently capable of sitting here listening to this deep dive and pondering your own atomic existence.
It is the ultimate paradox of the universe.
Exactly. How does unconscious mechanical matter wake up to study itself? How do the pieces on the cosmic chessboard become aware that they are even in a game?
It is a mystery that physics hasn't solved yet.
And it might never solve it, but it's certainly a thought worth wrestling with the next time you look up at the stars, or, the next time you just blow on a hot bowl of soup. Thanks for joining us, and we'll catch you on the next deep dive.